Hello, welcome back to, I guess, Stat 3050, but not really because this is no longer part of the curriculum. But this video here is going to be on random forest regression. So I'm going to be using the same data that I used in the decision tree video, so it's the grad school admissions thing. We knew that. Actually, let's just go back and look at it. So, a quick review. Here we saw that linear regression looked decent in the model output, but the residuals were garbage. So, we'll just look at that real quick. Cool. So that's what the residuals looked like. Not super great. I'll pull this up so we can see the model output too. Everything here is statistically significant, but the residuals don't look good, so we don't care, right? So we moved on to a non-parametric test called decision trees. And what that does is that if we were to plot the decision tree model, we sort of get this. Oh gosh, I have to run all of this again. Sorry. Cool. So we kind of get this, randomly sampled values and how they are related to the algorithm that is used in the model. And we know that the residuals of a regression tree or a decision tree will always look fairly decent. Again, we don't need them to look decent because we know that the decision tree is a little bit robust. Okay, so oftentimes decision trees are nice because you can visually see more or less sort of what's going on, right? At least on the general side of things. However, the biggest kind of downside to them is that if you were to add more data and it's a little bit different than what was originally seen, then the decision tree sort of trips up a little bit. Just because you have one tree that is sort of basing everything on. Again, it's more robust than regression because you're not kind of bound to a line here. You're using an algorithm instead. But if we were to include a bunch of different decision trees that use different sort of root nodes here and different nodes with different terminal leaves, well, then maybe we'll have a stronger model, right? Well, that's exactly what we're going to do. So in random forest regression, essentially, we're just taking a bunch of decision trees that are slightly different and then coming up on sort of a final conclusion. So, woof. They're very cool. They do require just a little bit of additional coding, but that's all right. So we have the tidyverse in, and then we have our new library here called Random Forest. We run that. I've already got everything sort of read in here, so it's all the same as last time, right? So we have our training data, our random number of row names, row values to use for training and testing. It's also like big time thunderstorming right now, so sorry if there's any rumbling in the background. And then we have our set C to run that just to make sure. And then we're all set, right? So I'll do all this again. Cool. You'll probably notice that a lot of these values might have changed. I don't know if that's because I forgot to set the seed, but I think it is. All right, so let's just get into it. So RF regression here, random forest regression. It still uses all the same sort of notation as linear regression model building and decision tree model building. So we'll just call this RF model, call it model 1, and then we'll use our new function here, random forest. Okay, and so it gets all the usual stuff. So it's going to be the formula. The formula equals the chance of admit as a function of everything here. And then the data is going to be the training data. And then, this next thing that we want is this proximity equals true. This is more or less useful in classification trees, but it's always good to get in the habit of putting this. This just sort of corrects for non-important and important variables included. So that's all good. If we were to run the summary on this, this new model that we built, we get this gross list of nasty, nasty things, right? This literally tells us nothing as far as the adequacy of our model. And this is one thing that is kind of frustrating. I think it's inconsistent. But in this case, we can actually just run the model itself. And then that's that. So now let's take a look at it. Okay, cool. So we have our call, right? This is just the original formula. And then we have the type of random forest, and we're doing regression because our outcome is some continuous variable. If we were doing classification, our outcome would be a 1 or a 0 or some character or something like that. And it would, instead of saying regression, it would say classification. Okay, now the number of trees. So essentially what that's doing is it's just making, the default is 500. So it's just making 500 decision trees, putting them all together, and then using that as sort of the overall model, right? So what it's doing essentially is that it's making it's trying a bunch of different models, a bunch of different decision tree stuff, and then when we try to predict a new value or something like that, it's going to put that into every single regression decision tree model. It's crazy. And then it's just going to take essentially some iteration of all of the outputs of all 500 models, which is so cool, I think. Cool. The number of variables tried at each split. Okay, so that's just looking at 2 of the variables in this case, and then saying, okay, which one tells you more of the story? And in this case, we can change this, and we will in a little bit, just to kind of fiddle with it. And then already we see that we get a mean square error, right? Mean square of the residuals of 0.0047. Now that's less than our original decision tree, so that's good. And it's also less, by a little bit of our linear regression model. Again, the linear regression model not the most helpful because our assumption was not met as far as the regression residuals. One thing I am curious, and so this percent variance explained, we can call that r squared. In this case, it's not a mathematical r squared, so that's why they're saying it's percent variance explained rather than putting r squared. When I am curious, I haven't actually done this yet. I just want to see what the r squared looks like for our regression model. Yeah. So our regression is the adjusted r squared is 80%. So it's saying that 80% of the variance is explained by the predictors. Whatever. I think the difference between 80 and 78.6 is literally 1.4. But I don't think that's enough to warrant saying that one is better than the other. Because we already know, again, the regression is not the best. All right, cool. So if you can believe it, that's kind of it as far as the bulk of random forest. But we still need to optimize this because we don't know if 500 trees is enough. And we also don't know if maybe trying more variables at each split will give us a better story. So here's what I'm going to do. I'm going to plot the MSE, okay? And we're actually able to plot, we'll just use this base R plot. If we just put in our model, what it's going to do is it's going to default to a plot that looks like this, okay? And so what this is, it's the mean square error on the y-axis, and it's just the number of trees on the x-axis. So we kind of see that as the number of trees increase, the mean square error decreases, right? And we sort of see that it kind of jumps around here and here and here and goes out. Now, do we know if adding 500 additional trees, so total number of trees being 1,000, is that going to go down? Do we know? Well, let's try. So here's a big thing. This can be pretty intensive on optimizing. Yeah, that's right. Sorry. I was talking and typing at the same time. So anyway, this can be pretty intense on the computer, on the processor. So I have a fairly decent laptop. If you don't have a fairly decent laptop, it won't crash anything, I don't think. but it will take quite a while to run, especially if you have a data set that is huge. And oftentimes in data science, we do. We have so much data available to us, and I'm talking like, millions of observations rather than just, a few hundred. Even a nice, decent computer will take a long time to come up with a model based on 1 million observations. So just kind of keeping that in mind, that if it's not running as fast for you, that's totally normal. Okay, so let's optimize. And I say optimize, we're actually just going to be exploring too. Okay, cool. So I'm going to copy and paste this RF model. I'm just going to call it RF model 2. And the only thing I'm going to change in here at first is I'm going to see the number of trees and how that changes. So I'm going to do 1,000 trees. Run that RF model 2. We now see that, let me compare. Variance explained is 78.6. We see that it's gone up quite a bit. And by quite a bit, I mean by barely. It's 78.94 now, which is, fine. The mean square of the residuals is honestly about the same, only 0.0047 compared to 0.0046. Oh yeah, not great, as far as an increase. So we'll just plot this. We'll see now that still the same thing, and we see that it for the most part, it does just sort of flatten off, right? I am curious. This might blow up my computer. I'm going to try 10,000. Buckle up. I'm trying 10,000 trees. So if I run that, oh yeah, it's taken a while to think. And I'm just going to go ahead and type this. Okay, it's done. So again, I don't want to brag, but I have a pretty good laptop. That took, 10 seconds to do? I've tried this on my other laptop. I have a MacBook, and I tried it with 10,000 trees too. And it took like 3 minutes for it to come up with something. The MacBook is older. It's from 2013, I think. So it's 7 years old. But again, it's going to vary among machines. So anyway, now we've tried 10,000 trees. The mean square of the residuals has gone down, I think not at all. Gosh, just barely. And then we're now at 79.01%. So if you wanted, theoretically, you can get up to, way higher values at the expense of, one, your computer and the number of trees that you're trying. So if I plot this, we don't really have a whole lot of evidence that it's going down all that much. It is going down just a little bit. So I'm more of a fan of just keeping it at the default 500, which is fine. We know that the difference between a mean square error of 0.005 and 0.0049 is really not that much. Nothing to, call mom about. So, okay. Here's what I'm going to do. I'm going to get rid of this just so when you're doing it on your own, it doesn't blow up your computer. And what I'm going to do, I'm going to take this, just bring it down here, because we haven't even tried predicting yet. Oh, you know what? And what I actually haven't even said is how this error is being calculated. So it's sort of doing its own internal cross-validation. So it's just taking out one observation at a time, predicting it, and then doing it again for another one, and then doing it again for a bunch of different combinations. And then that's how it's calculating the mean square error. So the next thing I want to do is I just want to try doing a bunch of different variables, trying a different number of variables at each node. So we do that by doing this argument mtry. Okay, so the default is 2. Let's just try 3. I'm also naming it the same thing. That's fine. Cool. So we see now that, let me actually just do this. So 79.11 is the variance explained when we have 2 variables, and then it's 78.49 when you try 3, right? So including more actually doesn't really help as far as 3 goes. See, and the more variables that we start including, the more the variance goes down, right? Because if you recall from the decision tree, it said that there was only two variables that really were used, and it was GPA and the GRE score, right? So it's probably doing the same thing here too, and I'm just going to explore here. Yeah, cool. This is very cool. So what this tells you here, this importance, this is telling you, it's using this sort of weird purity calculation, or this purity value, but essentially the higher the better, right? The higher the value, the more, the easier it is for the computer to make a decision about the next decision to make in the tree. And we see that GPA in undergrad has a high value, and so does GRE, right? And the next one is the TOEFL, the language. The language test. Cool. Man, sorry, I seem a little scattered. I have been at this for a while. Truthfully, I haven't done this in a while, so I had to do a whole ton of refreshing. And I still kind of am refreshing now. All right. Cool. So I feel pretty okay about this. So we're doing a model with two variables at each try, and those two variables are most likely the undergraduate GPA and the GRE. And then our total forest has 500 trees, which is pretty good. All right, so let's get into, let's just try predicting now. So predict, and then the object is going to be our RF model. Whoops. Okay, and then new data, again, new data is going to be the testing data. Cool. If we run that, sorry, we got to save that as something first. My bad. The testing data. Yeah, testing data. We got to save this. Predicted RF. Oops. Cool. All right, cool. So that's all good. The predicted RF is down here. It's 80 values. Yeah, that's good. Cool. And then we can calculate the mean square error. So we'll say it's the predicted values, minus the testing values, the actual values, squared. And it's effectively the same value that we got when it was doing it on its own within the model, which is pretty cool, I think. So that's a mean square error of 0.0046. So it's more or less just kind of saying that less than 1% of the time, it's wrong by a super small margin, which is pretty good. If we want, let's go ahead and let's plot this. What I'm gonna do is I'm gonna take the code that I did earlier. Gosh, cool. You're gonna hate this. Oh Lord. All right. So that's all fine. That's all good. Okay, we don't need that. That's a totally different thing. So again, we'll just make this comparison data frame. This is good to see too, because making data frames is actually, a pretty good thing to know about. So it's the testing data, and then the chance of admit. It's the actual value, and then the predicted. Again, these are just the column names. I'm not doing anything special here. And then it's the predicted values. Got that. If I knew how to spell. Cool. All right. And then we just run that. Cool. Now, this is interesting, I think. The decision tree actual versus predicted, we saw that it was kind of the stepwise function, right? But in this case, we see that it's a little bit less of a stepwise function, and it's more or less kind of equally spread out, right? We're able to get a little bit more precision with the random forest than we are with the decision tree, which is pretty cool, right? However, we still see that it does have that same kind of S-shaped curve that we saw earlier in the decision tree, which is fine. I would say that the random forest is probably a better thing to use, just in general. The only downside, well, there's a few downsides. Mathematically, it's all fine. I think that it's very intense on the computer, so that could be a downside. But the biggest thing is that explaining how random forests work to somebody who's not familiar with it, that's kind of tough, right? Decision trees are a little bit easier to explain, and you get that nice sort of decision tree plot, but you don't really get that with the random forest stuff. In fact, really the only thing that you can report is the mean square error based on the predicted or based on the model mean square error. It's like, that might be a little bit understandable, but that's really about it, right? You don't get any p-values. You can report the importance, what we see here on line 59. You can do that, and that's totally fine. You could say that, let's see, the undergraduate GPA contributes the most, and then the GRE is sort of next in line. I think if we were to look at the regression model, it would say about the same. And we can base that on the p-values too. So let's take a look. Undergraduate GPA, the p-value is nearly 0. And then the GRE is also fairly small, right? So, this is a little bit inaccurate because our residuals didn't look great. I think that in this case, if residuals never look good and there's really nothing you can do, try using decision trees or try using, random forest stuff, because they are non-parametric, right? They don't need to have, normally distributed data. Not that regression does, but what regression requires is normally distributed residuals, whereas that's not even a question with these non-parametric stuff. So, is there anything else I want to do? I am just sort of like trying a bunch of different things right now. So if you have any other questions too about if I left anything out, because I don't do this all the time, but if I left anything out, let me know. Another thing we can do is, so let's go back here. Whoops. All right. Okay, so 500 trees. What we can do too is we can see which number of trees results in the smallest deviance or mean square error in this case. So we just use that which min again. And in this case, it's actually a little bit easier to do it. So this RF model, we'll use the $sign here. And then the MSE. And let me bring this up to, where'd it go? I'll just rewrite it. Plot of the RF model. Cool. So what it's going to do is it's going to look at the error, it's going to find the smallest one, and then report back the number of trees that it corresponds to. Which I think in this case it would probably be like 420 something. I know that's the number, but I think that it would be right around there. Yeah, 431. So it's saying that if you wanted to make it the easiest on the computer, just include 431 trees rather than all 500. Again, I'm just sort of dicking around right now, but let's try entry. Let's go back to 1,000. We'll do that. We'll see that everything does change just a little bit. We'll plot it. Now let's see which min. Now it's 848, right? Which min would that be? Well, that's when we would have to break out that sort of complicated looking line of code. I'm not going to do it just because this function and all this model building, it's pretty robust. So there's not really a whole lot of fiddling that you have to do once you get kind of an idea of what to change in here. And so let's actually, just for fun, since we have time, and you can hang up whenever. Oops, that's not what I wanted. Let's just look at the options here. I think that there's some interesting things. So you can either use the formula for like the regression formula so the outcome as a function of a predictor, or you can just put in the matrix for the predictors and then the matrix for the outcome. Again, whatever. Or I guess it's a vector, not a matrix for the outcome, since it's just one thing. You can, interestingly enough, I don't even know what it would look like. If you leave out y, it'll just run an unsupervised model and just tell you what it can tell you about the data, which I think is pretty interesting. Blah blah blah. Let's see. Entry, we did that. Mtry, we did that. Replace, again, if you want to. When it's doing the MSE calculation internally, you can set it to where it would replace the value rather than not replace it, whatever. So that's illogical. Blah, 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 blah. A lot of this is used for, let's see, classification. And let me do this too. Let's see if this... Does that tell us anything different? No, it doesn't. We still have to... Ah, nice. Cool. Sorry. So when you include an importance in the model here as an argument, it'll give you still that purity value, kind of weird. But then it'll give you this MSE. And again, it looks like, the higher the better. They're all still pretty low. But again, either way, I would use this purity value just because it's a little bit easier to see that GRE and undergraduate GPA. And I guess the TOEFL all kind of contribute fairly decently in this model, right? Cool. Let's see. Oh, cool. Yeah, so a lot of this is used for when you're doing classification. So trying to figure out like an event, a 0 or a 1 or more than that, 0, 1, 2, 3, 4. Those could represent, some outcome, some categorical outcome. Again, that's sort of outside the scope of this class because it's always good to understand how logistic regression works first before getting into that. But I'm just sort of tooling around now. Cool. Oh, I love that. So what it's doing here, this do trace, it's going to print out, oh man, it's going to print out the mean square error and then what looks like the number of trees it's trying. And then, oh man, I don't know what this is. Let's see. I don't know what that is. Boy, that's something though. Pretty cool. All right. Okay, so I think that's about it, I think for now. So, okay, one last thing. There is a function in here called rf impute, okay? And so let's actually take a look at the help documentation for this, because it's really interesting. So decision trees and random forest regression can be used for, figuring out some outcome, kind of predicting some outcome. And usually only prediction. We don't really care about how things are related when we get into these data science sort of methods. But what you can also do with decision trees and random forest, or you can use those models to replace missing values based on the other values in that column, right? So I think in your final, with the bare data, there are a few missing values in there. And so with that, if they're continuous, it doesn't matter how they are distributed, but if they're continuous, or just integers even, you can run a random forest imputation on that column, and it will replace the missing value based on a random forest regression or decision tree regression, which is super cool. So you can use this function to do it, and then it will replace it. All the details are in here. Tells you a little bit about the algorithm and whatever else. It's just really cool. It uses the whole data set, and not just the individual values in the one column. it'll look at the outcome. It'll look at how they're related to all the other predictors too. It's super cool. It's super cool. So yeah, you can actually run this. If you copy and paste this code in here, it will. This is a dataset based in RStudio. It's already in here. It'll run and work pretty perfectly. So anyway, that's another tool that you can use for random forest stuff. This is a pretty casual sort of review, or at least insight into data science and these more complicated quote unquote models. I think that this stuff is really cool. Again, it can be a little confusing if you're comparing this to regression. But for now, I would stick with these two if you're trying to get your foot in the door. And then when you want to move on, I'll make a little list here. You have k-nearest neighbors. Technically, logistic regression is machine learning. Pretty cool. Gosh, what else can you do? There's this thing called ridge regression. That's a little bit more complicated. Oh, man, there's so many different things. There's a really cool one called naive Bayes. Now, I'll get rid of this because this is sort of its own thing. What these all do is they all predict some event from happening. Not from happening. It predicts an event happening or it not happening. Whereas you can use random forest and decision trees for regression or for event prediction. Pretty cool. All right, cool. So with that, that's going to be it, I think, for now. If you have any other questions or want me to make other videos about these, totally can. There's a whole class here that goes into logistic regression called categorical data analysis. Pretty cool. I actually misspoke. There are a few other classes that do machine learning stuff here. They're in the computer science department, so you can check those out too. So you can get a real professional. I'm a statistician through and through, so I'm more of a regression kind of person. But if you want a real machine learning pro teaching you, I would look into those classes. But with all that being said, I'm going to call it there. So I will see ya when I see ya.